Good morning, everybody. Welcome on the third seminar this year, the seminar of Quantum Information and Quantum Computing Working Group in Warsaw, CFT, Polish Academy of Sciences. Today the speaker is Sébastien Designolle, and the title of his talk is Bell and Grothendieck meet Frank-Wolfe. Sébastien, please, the Zoom is yours.
Thanks, Wojciech, for the invitation for the introduction. I will tell you about a series of I think now 3 papers over the last 2 years. Some of you have already heard about the first one, but since then there's been some extension, and they basically revolve along like two major lines. The first one is familiar to some of you. It's the connection between Bell nonlocality and Grothendieck constants, but this will be the topic of my first part. Then I will present the Frank-Wolfe algorithms, a family of algorithms that are used to optimize over the local polytope. And finally, I will present you the results, namely better bounds on Grothendieck constants of finite orders. And these bounds have implications for Bell nonlocality. Let me start from the Grothendieck side, actually, because you're probably less familiar with this. And I will do this quite formally by introducing this quantity, this SDP d of m. So d is an integer from 2 to infinity, and m is a matrix, not necessarily square. It's just a real matrix. And this quantity SDP d of m is defined as this optimization problem where my a and my b live on the sphere in dimension d. So typically, if you think of d being 1, then these a and b are just plus and minus 1, and this quantity boils down to the local bound of a correlation Bell inequality. So you will quickly be back on your feet, even though the notation sounds a little bit unusual at first. And to make this really smooth, let me give you directly an example that you know, namely if the matrix M is actually the matrix A here. And in this case, you can just enumerate the different configurations that are possible for D as 1. And those configurations correspond to deterministic strategies that you're all familiar with, but now with a kind of slightly different framework, let's say. So these are the different matrices, and the maximum then, this maximum here, is 2. But now I can turn my attention to a higher d, namely when d is 2. And in this case, I'm not proving it, but I mean, you kind of know how the proof would go. There is an explicit strategy of vectors. They actually form this rotated bases, and these vectors A and B define here a matrix of scalar products who's in turn giving an objective function of 2 square root of 2. And with this, we recover the standard ratio between those 2 quantities, which is square root of 2. And it turns out that this value of square root of 2 is actually generic, in the sense that if you give me any matrix, not only 2 times 2, as I've just given as an example, but any matrix will actually satisfy the fact that the ratio between this quantity for d is 2 and this quantity for d is 1 is bounded by square root of 2. And this is actually the best upper bound possible on this ratio here. So more formally, we say that the Grothendieck constant of order 2 is actually square root of 2. Feel free to interrupt at any time, by the way. Presenting online is a format with which I'm not completely familiar. So yeah, let me give some feedback if anything is like too slow, too fast, or unclear.
Okay, will do.
The things around those Grothendieck constants, even though they seem a little bit like easy because the two-dimensional case was kind of straightforward, even though I didn't prove anything. The problem is that when you go to anything but dimension 2, the values of those constants are not known. And I've compiled some known values of the Grothendieck constants of order 3, 4, 5, 8, and infinity. And the gist of my talk is that in the course of the last 2 years, I've improved some of those constants. As you can see, some of them only a little bit, like this one, some of them a bit more. And for this one here, there is actually going to be an asterisk later, namely that it's not completely proven. But let me not anticipate.
What about dimension 7, because it's missing in here?
I'm not putting it on the slide because the only bounds that we get are kind of implied by monotonicity.
Okay.
So typically, this is the best lower bound on dimension 7. Okay. Implied by the results. So I did not put it on the slide itself. But yeah, the results improve on what is known on the 7-dimensional bound. Why do I care about these Grothendieck constants? So as you might have seen, I'm now in an institute that is mostly doing some optimization, this Zuse Institute in Berlin. And this kind of question, this kind of constants, they actually show up in the context of approximation factors in some relaxations, especially in the context of this max cut problem that I'm not really defining, but somehow there's a link that some of you might be aware of between these constants and some approximation theory. I'm not going to dive into this, but will motivate the next the result that I will present by the connection with Bell nonlocality, which is what I'm going to tell you now about. So as you probably know, the threshold for the nonlocality of the 2-qubit Werner state is exactly the inverse of this Grothendieck constant of order 3. But this connection actually generalizes to more dimensions, to higher dimensions. And for the moment, in this first part and in the second part, apart from the results that I've just kind of first spoiled a little bit, everything is kind of known, and these are connections that and algorithms, as I will present later, that I have not developed, but that I have successfully applied to the and scaled up to the case of higher order Grothendieck constants. So let me remind you a little bit the link between Grothendieck constants and Bell nonlocality. As you are familiar with Bell nonlocality, I will just quickly mention that when Alice and Bob share some classical resource, lambda, then they have access to a specific set of points in this probability space that forms a polytope when we are in a finite scenario. And when they share a quantum resource, they can actually get points strictly outside of this polytope. And this is the essence of Bell nonlocality. In the rest of this presentation, I will go for the dichotomic scenario in which the outcomes on Alice and Bob's side are actually plus or minus 1, so that I will not work with this probability tensor, but only with this correlation matrix here, P of x, y. And for pure states, this is basically the entry of this correlation matrix. And if I go a little bit more specific again, and I say, okay, now I have the psi minus state, so this Werner state of 2 qubits, then this correlation matrix actually has a very specific shape, namely this scalar product of ax and by with a minus sign, which is kind of irrelevant. But this is the reason for the connection between this this Grothendieck constant of order 3 and the threshold for the singlet state. Why? Because when you actually compute the value of the local bound corresponding to this, you're restricting your A and B to be plus or minus 1. Whereas the correlation matrix that is obtained quantumly is for A and B being on the Bloch sphere and then having access to more resource in terms of dimension. So in a sense, if you just think of the Bloch sphere, a classical strategy would just live on a line, and a quantum strategy lives on the entire sphere. And you have the intermediate scenario when you restrict Alice and Bob to only do measurements in the plane XZ, let's say, like real quantum mechanics. And we will talk about that a little bit later. But first, in the case of this Werner state, there is an exact correspondence between the Grothendieck constant of order 3, because here this is the three-dimensional, I mean, the sphere in dimension 3, and the non-locality threshold. But this connection can be extended. If now my vectors A and B, they do not live anymore specifically in dimension 3, but potentially in higher dimension, in dimension D, then if I choose an N such that there exists a basis of anti-commuting operators in dimension N, so typically you will take like Pauli strings in dimension 2 to the something, 2 to the d over 2. And this, with the Maximilian tangle state and these specific measurements, actually gives an explicit quantum state, namely this state, and quantum observables that have this exact correlation matrix. Note also that correlations are marginals are 0 in this case, because these matrices are also chosen to be traceless. And with that, I can sketch a little bit more specifically the connection that was stated in this paper by Essine, Gisin, and Tonner in 2006, I think. Namely, okay, I have to explain a little bit what is in this table. I will start with here. So there exists, if I consider the Grothendieck constant of order 3, there exists for the visibility 1 over this constant a violation, and this is precisely the question of this threshold for the Werner state. But it also turns out in dimension 2 that we have an LHV, so an exact model for the Werner, or in this case the Maximilian tangle state in dimension 2, that precisely goes up to this 1 over Grothendieck constant of order 3. So you see here, this corresponds to violation. So when I have a visibility that is higher than this inverse, there is an explicit violation. And there's an explicit model when I'm below this visibility here. And because those two numbers coincide, in the case of dimension 2, the visibility, the critical visibility for this state is exactly 1 over the Grothendieck constant of order 3, which is the result you know.
Can I have a question? Can I have a question? So the LHB model you are talking about is like for projective measurements, right?
To be more precise, it's for traceless observables.
Traceless. Yeah, but is it different from projective measurements?
In dimension 2, it's the same, but in higher dimensions, it's going to be slightly different.
But you can always represent a projective measurement in terms of traceless observables, right?
But projective measurements have more than two outcomes, right?
Yeah, so for instance, you have three outcomes, and then you can construct observables which are traceless. You just have to properly name the outcomes, right? Okay, but like in any case, I wanted to know whether this is for the projective measurements. So,
yeah, it's working for projective measurements, definitely.
And okay, the other question, just understand, so like in the Grothendieck constant, you take into account only the inequalities that have like correlation terms, right? I mean, so that they don't have local terms, local expectation values.
Exactly.
Okay.
Yeah, I take marginals to be 0 just for convenience.
Okay, thank you.
Later, I will talk a bit about the multipartite extension, and there I take the marginals into account because they no longer vanish. But okay, in dimension 2, you have this exact threshold that is both for LHV and violation of a Bell inequality. So this was for this here. Now, if I turn my attention to LHV for any state, not necessarily the maximally entangled state, the relevant Grothendieck constant is the Grothendieck constant of order 8. What does it mean? It means that now there is going to be a gap, right? Because the inverse of this Grothendieck constant is going to be strictly smaller than the inverse of the Grothendieck constant of order 3. So that for generic 2-qubit states, we will only have an explicit LHV up to the Grothendieck constant of order 8. And then there is somewhere where this connection cannot really tell you much more. Then I can tell you a bit about this 2 here. I'm just saying with this that the Grothendieck constant of order 3 being strictly larger than the Grothendieck constant of order 2, then the inverse are sorted the other way around. And this is precisely this effect that was first proven by Tomasz Fertesi with those 465 measurements, that KG3 can actually detect a bit more than CHSH. Because CHSH is nice, but it's only on the plane. So it's only using a 2-dimensional quantum strategy. So that it was for a long time a question to actually just detect more with 3-dimensional strategies, but now it's definitely a question that we have answered. By the way, note that the smallest example for which we actually have a better violation than CHSH using then 3-dimensional strategies involves 11 questions on Alice's side and 14 on Bob's side. Okay, and this Grothendieck constant of order 8 is also important for the maximally entangled state in dimension 3. Unfortunately, in this talk, I do not improve on the bounds on this constant, at least on the relevant bounds to get better LHV in those 2 cases. But I still wanted to mention this connection. What I do improve on the other side is that are the bounds on the Grothendieck constant of order 4 and 5, and these provide then better violations in dimension 4. Namely, you have 2Q quartz system, and then, as I can show you here, this was the best lower bound on the Grothendieck constant of order 4, which is now, sorry, I was speaking of this side here, which is now strictly smaller. So there is a better violation. You can say it's marginal, and it's indeed the case for the Grothendieck constant of order 4, but for the one of order 5, then the difference is actually more significant. I will also later comment a little bit on this difference here, because between those 2 numbers lies precisely the CGLMP visibility, but more on that later. If there are no more questions, I will give you a flavor on how to derive bounds on those constants.
Perhaps I would have a question.
Yeah.
So concerning the higher dimensional case where you have more outcomes than two, I remember that if you would like to represent the measurements in terms of observables, you have to also include the powers of those observables to be like in one-to-one correspondence between, you know, probability distributions and the expectation values.
Yes.
And this is not included here, right? Because you just take the, you know, just the observables, like the tensor products of the observables themselves, not with the powers.
Yes, I would say so.
Okay, because maybe if you included the powers, so that, I mean, you know, then maybe this would somehow change the bounds in the Grothendieck constant, or maybe there is another constant that should be, you know, included here.
So it sounds definitely interesting. I'm not sure I really see what you're talking about with those powers. Do you mean something like the NPA hierarchy, or do you have something different in mind?
It's just that if you, in the qubit case, if you have like PABXY, you can represent it in terms of the expectation values of tensor products of observables plus the local terms, but now you assume that the local terms are zero. But now if you go to like more outcomes, you will have more probabilities than expectation values, right?
Yes.
Okay. And so somehow, if you go to the expectation value picture, you don't have the full knowledge about the experiment. And to properly somehow map the probabilities to expectation values, you have to include the powers of the operators. And then the mapping is one-to-one.
I see. So maybe one thing that I can comment is that the approach that I'm going to present just afterwards is not restricted to two outcomes.
Okay.
So maybe it's easier to directly work with probability distributions, like probability tensors.
Okay, so let's see. Thank you.
Okay. But
so,
yeah.
Hello, here's best regards from Krakow. Here's Karol speaking. I have a very naive question, in a sense trivial. So some time ago, I was trying to learn something about those Grothendieck constant, and I tried to memorize some numbers. So why you work with inverse Grothendieck constants? Is it easier for you to speak about 1 over square root of 2 instead of square root of 2?
I did that today before the talk because I thought you would be more comfortable with the inverse of the constant.
Ah, okay. No, but in some tables in Wikipedia and other places, usually people work with Grothendieck constant. Okay, but thank you.
Yeah.
But no, but from the pragmatic point of view, which convention is easier, suits you better? The same, yes, of course.
I must admit I have a little bit more intuition on the inverse side because it has this meaning of visibility.
Okay. No, it's a good point, because in mathematics, usually this convention is more well-known and established, but maybe it's from the physical perspective, okay, it's a matter of taste, of course, but good to know both. Okay.
Yeah,
Thank you.
I like the fact that, like, typically this infinite constant amounts to a visibility of, okay, at most 0.59. I mean, I can grasp that a little bit better than the 1.70 something from the other constant. But this is a matter of habit, I would say. Sure. I mean, I started with this constant and I really worked a lot between those, and then I just got used to it.
Okay. But this number 0.5963, okay, of course, it could be improved somehow, but it will play potentially some role in physics?
Yeah, the role in physics is that when you actually go to infinite dimensional systems, this is here. This is the best you can currently do with the bound on the Grothendieck constant of order infinity. So there exists a dichotomic Bell experiment that is robust up to this point, which is kind of nice when you compare to CHSH and standard experiments, right?
Yeah.
I mean, typically two-dimensional systems, they cannot do better than this for sure. Sorry, this new bound. And yeah, infinite dimensional, they can definitely make a point.
No, and of course, what is nice is to give to Grothendieck constant such an important mathematical notion, some physical interpretation. This is very nice. Thank
Again,
you.
this is not my work. This is
Yeah.
Assin, Duot, Gisant, and actually Tirelson was the first to notice this, but without the explicit connection with Grothendieck in 87.
Thank you.
Okay, so now I'm going to tell you a little bit how to obtain bounds on these Grothendieck constants. And what I want to convey now is really the geometrical aspect of this proof. Why geometrical? Because in the end, there is a polytope involved, this local polytope. And what's important is to actually get a quantum point, or let's say a d-dimensional point, that is as far away as possible from this local polytope. To put it in a bit more formal way, the local polytope is responsible for this denominator here, this one, and the numerator here, d, we actually want this to be as big as possible, because getting a lower bound on this number here is just exhibiting, so to speak, a feasible point for this problem. So finding a matrix M, that is actually quite good. And it turns out that one way to get such matrices is to try and come up with facets or things that are as close to facets of the local polytope as possible. And I'm coming back to the CHSX example because it's pretty good to geometrically understand what's happening. So as I've shown before, the local bound, so the SDP1 of this matrix A is 2 precisely. And what I've also given before was an explicit construction with vectors, two-dimensional vectors A1, A2, B1, B2, that was actually giving a lower bound on SDP2 of A. Back then, I just told you this is equal. Now I'm just claiming that it's at least this value, and now you can trust me because I'm not telling you anything wrong. I'm just saying I had a point for this, and these ones I enumerated. So this is an equality, and this is an inequality. But if I combine the two of them, I actually get a lower bound on the Grothendieck constant of order 2. Now I'm not claiming anymore that this is an equality. I mean, it can be proven in the case of the Grothendieck order of order 2. But what I'm going to do now is just to say, in order to get a lower bound on the Grothendieck constant of order d, I only need to explicitly compute the local bound. This is the hard part. And I need a good construction of points that give naturally a lower bound by definition of this problem here for dimension d. And by doing so, by construction, I have a lower bound for kgd. Geometrically, this amounts to starting from a point here and trying to get this facet. And okay, even though this is now how I've defined it, so starting from those vertices to define the facet and then separate the point A, the way that I'm going to do it now is kind of starting from the point and then projecting it onto the polytope, so that I don't need an explicit list of all the facets. I just need the specific facet that is separating this point, this blue point, from the red local polytope. And once I have this projection, then the vector from this projected point to the point, the blue point P, is exactly my facet. To get some upper bounds on the Grothendieck constant, it's a bit less trivial because these are not the bounds that you get from the definition itself. So I will go a little bit faster on this, but I'm happy to answer questions on this later. But the idea is to start from a point P that corresponds to strategies here in the sphere that kind of cover the sphere well. And this covering radius is then used to approximate, in a sense, the entirety of the sphere. In the case of this two-dimensional example, it would give the dummy bound of 2 square root of 2, which is not good at all, but it's just to kind of give you an idea of the method. So the method is to kind of cover here the circle with finitely many points, and use the shrinking factor of this covering, of this approximation, to derive upper bound on what's generally possible for any matrix, not necessarily a finite sized one. Okay, that was the first part of my talk, drawing a little bit the connection between Bell and Grothendieck. But now let's go a little bit in the world of Frank-Wolfe, so in the world of complex optimization. And let me describe, how I was able to, in the end, do a little bit better than what's done before. The essence of what I've done is to project, as I've said, a point outside of the local polytope onto the local polytope. And the thing that is going to be difficult is that the dimension is going to be fairly big. But above all, the number of vertices of this polytope are going to be extremely large. And because of this very, let's say, hairy complexity of the local polytope, it's important to stay inside it, because as soon as you go out, you don't really know how to come back, because this is precisely the problem that you try to solve. And this idea of staying inside the feasible region is exactly what Frank-Wolfe algorithms are doing. The original algorithm, I'm going to present it to you right now, completely amounts to what was done before in the literature. The idea is to do kind of a gradient descent to minimize this distance function between the local polytope and the target point. And because we have this specific objective function, the gradient is just, or the negative of the gradient is just going from the current iterate to the target point. And as I said, if I follow this gradient, I might go outside of my feasible region. So I absolutely want to stay inside of my feasible region. But I still want to do some progress. So in order to do progress while staying in the feasible region, at each iteration in this original algorithm, I solve this linearization of my problem. So instead of going to the gradient, I go to the best point in the feasible region that is aligned with the gradient. So as you've seen before, with this random point here, I was only going up to here on the direction of the gradient. And now I'm going actually up to there, which is basically the best I can do. It means that the so-called linear minimization oracle in this Frank-Wolfe framework is going to send me to this point, or at least in the direction of this point. And then I just have a quadratic function to optimize over this line, and I just find the best solution. There is an exact form for that, which is this x1. And I just repeat that. Now the gradient is going from x1 to x star, and the best direction is this one, and I just stop on this line here. And I just do that again and again. And I converged to the projection of x star on the local polytope. As you can see, this is working, but this is also quite slow, because the more we advance in the algorithm, the more susceptible we are to get this zigzagging behavior, namely that the direction of progress is going to be orthogonal to the gradient, so that we basically do almost no progress at all. But this is still what was done in the literature of quantum, of Bell nonlocality, calling the oracle at each iteration, doing a bunch, like a few millions of iterations, and hoping to get closer and closer, but still having this zigzagging issue, and also calling the oracle all the time. The idea behind Frank-Wolfe algorithms is to find better ways to deal with this kind of problems. Better ways in the sense storing some information along the algorithm that can be used in a smart way. And in this case, I will guide you through the so-called blended pairwise conditional gradient algorithm, which is an adaptation of what you've just seen, so the vanilla Frank-Wolfe, where I keep in mind all the vertices that I've visited, or all the vertices that are building the current iterate. Let me show you that. These vertices are going to be in red. So I start again from x0, and I follow the oracle to go to x1. Now my x1 is an explicit combination of x0 and this vertex here. I have the weights, and I know how to create this one. I call the oracle again, and now I'm here at x2, and I have an explicit decomposition of x2 in terms of those three vertices. But now, instead of calling the oracle again, I can be a bit more, a bit better, and actually see that this x0 here is bad. This is what was pulling me back in the previous run. And I would like actually to not only do some progress in good directions, but forget about bad directions. And in this case, what I'm going to do is I'm not going to call the oracle. I'm going to say, oh, now the gradient is this one. Which one is the best in the three red points? It's this one. And which one is the worst? And this is this one, because it's definitely not aligned with the gradient. And this pairwise iteration is actually going to move along the line between this worst and this best point within the memory. And geometrically, moving along this line means to take some weight from this point and put it on this point. And it means moving parallel to this line. And again, I have a line, I have a quadratic function, I just stop at the best point on this line. But because I have an explicit decomposition of my iterate, I know I can never go outside of the subpolytope defined by my memory. And now I can redo that. So now the gradient is like this, and the best point is this one now, and the worst is this one. And now something interesting happens. Now, if I'm to move along this line, then I actually want to remove all of the points, all of the weight that is on this x0. And this I can see because the optimal point would be outside of this subpolytope, meaning that the optimal weight on x0 should be negative. I don't want to leave the polytope, so I just maintain this weight, or I put this weight at 0, and I displace the entirety of what was before on x0 to this vertex. And now I have landed on the facet, and the last iteration can converge to the optimal. That was a lot of speaking on my side. Do I have any questions?
Well, maybe I would have a question concerning whether this algorithm applies only to polytopes. Does it apply also to other convex sets?
It's a very good question. The answer is yes.
Okay, because like it seems that you could also try to use it for finding the best separable approximation to an entangled state, right?
So it's actually a direction that I'm currently exploring with a postdoc.
Okay.
But this is in the conclusion. That's exactly, yeah, that's completely valid. So we can do that, and it's working. We're writing a paper on that, but I'm definitely interested in discussing that.
Okay, thank you.
Other questions? Good. So yeah, let me comment a little bit on what I meant by best vertex. So this linear minimization oracle. So formally, I mean basically finding the local bound of the gradient. Because once I have a specific strategy that is optimizing the local bound, like a deterministic strategy, I will just go in the direction of this strategy. And then you will tell me, sure, but then you haven't gained anything because finding the local bound is hard. And this is true. I'm not saying this is not the case, but what I can do within the algorithm is to use a heuristic, because as soon as I'm doing some nice progress, this is fine. the algorithm is actually gonna converge because the heuristics are usually quite good. But in the end, I want a proof. And to have the proof, then I will need to call these beasts, like what Tamás has written and some other Cubo solvers developed here at my institute. And I need to do that only once. So this is the big difference. Within the algorithm, I call the heuristic LMO, basically doing some optimization on A, on B. I mean, you know how it works. And only at the end, I call the solver. And this is exactly what we've been doing. And with that, I can show you the results. So first, starting with the lower bounds. I haven't told you at all at the moment what I was taking for structures. And if you have in mind these Fishburne and Reed's paper, or maybe if you see a little bit the structure in those high number of settings inequalities from Tomás, you see that somehow it's good to cover the sphere, not only to get this eta that I mentioned before, but actually already to get some good violations. It's beneficial to cover the sphere, so the high-dimensional sphere, in a kind of good manner, like as
We don't hear you now. I think you're.
This is kind of the reason for kind of proxy. Oh, sorry, am I back?
Yes, now it's okay.
Yeah. So this was the reason for me to consider, in a first step, those kissing configurations. So the configurations of points in the d-dimensional space, such that spheres centered on these points touch a unit sphere in the center of the space. How many of them? In dimension 2, 6 of them forming a hexagon. So 6 of them, but only 3 lines, because I'm connecting antipodal points. Because they just correspond to one measurement in quantum words. Then in dimension 3, there would be several options, like you can consider the icosahedron or the cuboctahedron. Interestingly, they give different values of the threshold that they obtain. And in higher dimensions, this is exactly the Fishburne and Reed inequality that gives the 0.7 visibility. And yeah, so there is a bunch of inequalities that we could derive. All of them are facets. And there's a little bit of an explanation that is required. I was able to derive facets of the symmetrized local polytope, in the sense that all the computations that are done, somehow they respect the symmetry of the initial point. And if my initial point is this kind of 600 cell, for example, then everything will somehow happen in the subspace that respects this symmetry. So that what I have in the end is a facet, but for this symmetrized polytope. So it does not necessarily is a facet of the full correlation polytope. But still the best you can do to detect those symmetric structures. And the second thing that I would like to mention are those asterisks here. They are kind of the biggest disappointment of this last paper, but they're also the biggest motivation of the next one. Namely that in spite of the huge symmetry of the instances that we get, we could not solve the local bounds of these big instances. And I mean, you can kind of see why. I mean, 300 settings is big. It's big, but it's also insanely symmetric. So my next big step in this direction will be to exploit this symmetry to get these asterisks away. Yeah. Because of this frustration of not getting the local bounds for these symmetric structures, we decided to put the elegance a little bit aside and try to do the best that we could do with Tomás solver. And it meant dropping the symmetry, so the fact that Alice and Bob have the same number of settings. And typically in dimension 4, having only 60 settings on Alice's side, but way more on Bob's side, meant that we could still solve the local bound with the branch and bound from Tomáš, but with a reasonably good bound. And this is the bound that is obtained. And as you can see, and as I mentioned already before, the CGLMP threshold, so the infinite dimensional one. So if you take CGLMP and you take the limit, you end up with this Catalan number bound. And this Catalan number is beaten by this inequality, whereas it was not the case before in the literature. So this is nice because it means that we can beat this kind of asymptotic CGLMP visibility only with dichotomic Bell inequalities. And not with the number of settings is still quite high, but the dimension itself is not that big.
Can I have a question here?
Yes.
So I'm a bit lost now because so the dimension here is the dimension of the system, but you always have two outcome measurements, right?
Yes. So it's a dimension of the real sphere. So if I go back to my it was here, yes. It turns out that dimension 4 corresponds to qubit, or not, sorry, but to quantum dimension 4 as well.
Mm-hmm. Okay.
So there is an explicit.
So you don't have measurements with more outcomes. It's always like two outcomes.
Yeah, it's always two outcomes.
Mm-hmm. Okay. And why compare it to the CGLMP where you have like many outcomes?
Because it kind of it could be that it's not the case, right? I mean, of course, with this in mind, you know that it's going to happen at some point. But seeing when it happens, I find it quite interesting. Mm-hmm. I mean, it's not a major kind of application, but it's just kind of nice to see that it already happens starting from dimension 4. Mm-hmm. Also because it was. Yeah.
Okay, please continue.
This is something that Tomáš was really into, so I kind of got his enthusiasm. I must admit that myself, I was not completely. I don't really know why he wanted that, but I know that for this paper, so this is Tomáš's paper, he wanted quite badly to get this, and he didn't manage. But he waited for 3 months for the local bound to finish in this paper. And I think this one took, it was like a day or something like that. Because it's way smaller. Okay. In a sense, here he has like 90 settings, and 90 settings is already like really big.
Mm-hmm. And concerning this number for CGLMP, I mean, it's like it's still unknown whether this is the I don't know. I mean, the maximal quantum value of the inequality is still unknown, right? I mean, it's like you take it from the supposed optimal solution, right? But
yeah, it's still unknown.
This number can still change, right?
Yes, it can change, definitely.
Okay. Thank you.
Yeah, a little comment on the 3-dimensional case here. In my attempt to cover the sphere, I just, to get those 97 measurements, started from a cube and kind of took the center of the faces, again, some edges, project them on the sphere, and do that repeatedly to actually end up with a structure that I twist a little bit to get the measurement settings of Alice and Bob. And in dimension 4, this is exactly the 600 cell, and this is the combination of the 600 cell and its dual. And these are like kind of more ad hoc constructions that come from Sloan's database online of good coverings of the sphere in dimension 5 then. Okay, let me just check how much time I have left. Oh yeah, perfect. So I'm basically almost over. So the only thing I wanted to mention is these upper bounds. As I quickly mentioned at the beginning, they rely on good approximation of the sphere. And the main difference is that now we don't want to explicitly separate a point from the local polytope, but we want a local model. So we want a decomposition of a point inside the local polytope. And for this, we don't need to have an explicit, so linear minimization oracle anymore. We can just do the entire algorithm with the heuristic one. And because it's giving an explicit decomposition at the end, we don't need more. So we don't need to run the QBO or the branch and bound even once. It means that we can access way bigger instances. And typically, what I'm using for the results is this covering of the sphere with like, it has like more than 2,000 points. And the results are entirely analytical. With this, I can recap a little bit the history of the Grothendieck concept of order 3, with CHSH on one hand and Werner on the other hand. This is the paper doing the connection with Grothendieck, and then results from the math community were imported, but then quantum people took over, and this is the current state of my computations, and this is the upper bound that was also step-by-step reduced, mostly by Tomasz. He's also there, and also again there, and also again in my work. And all of this also works for more parties. More parties. And in the initial paper, we did some proof of principle to improve on the entanglement threshold, and quite substantially. And with that, I can summarize, tell you that I definitely want to solve those symmetric instances, that I would like to get some interesting instances with more outcomes, because the code is working and is really efficient for this as well. But yeah, I'm just have to find a bit a way in the zoo of those higher outcome scenarios. I mentioned the entanglement detection already, and the last thing that I would like to advertise is the fact that all of this research is done in Julia, which is a language that I can really recommend, and for which we developed a package to facilitate your let's say your conversion to this new language, and we is with Mateus Araujo, who is the main developer, and other colleagues. Thank you for your attention.
Thank you very much for the interesting talk. Are there any questions or comments?
Well, I can have some.
Please go.
So in the multipartite case, how do you define the Grothendieck constant? Well,
How do I define it?
Excuse me?
Say it again. How do I define?
So in the multipartite case, how do you define the Grothendieck constant?
Then the connection is not really with Grothendieck constants. So there are some works doing some generalization of Grothendieck constants, but there, I must admit, I've not really looked into the possible connections with us. Also, because what I'm doing is state of the art on the Grothendieck side. So, I mean, the only interest of this connection would be to export that in those contexts. And maybe there are some people that would be interested then, but I haven't taken the time to do that.
So here you are trying to get the critical visibility under, like, below which you don't observe an entanglement, right? So that's
some certain non-locality, yes.
So is it for non-locality or for entanglement detection? No, this is
for non-locality.
Okay, so
so I'm giving you this W state, and what I can tell you is that up to the visibility of this, there is non-locality, and there I constructed an exact inequality, and then I could come up with a local hidden variable model for projective measurements up to this point here.
Okay. Oh, that's very nice.
Yeah. Especially because we worked so that there is a strict separation between the two. So this upper bound is strictly smaller than this lower bound.
Mhm.
Any more questions or comments?
Well, I can have another one.
Please go.
So since you said that this algorithm can be applied to find the best separable approximation to an entangled state, so you can I guess you can also use it for like for estimating entanglement measures, right?
Yes.
And is it faster than, I don't know, some other existing algorithms, or?
What would you have in mind in particular for entanglement measures?
Well, SDP, for instance. Some measures you can formulate in terms of SDP.
So I would say, so we have typically here in-house people that are developing SDT solvers based on Frank-Wolfe. So this is working. I should maybe have said a little bit what are the advantages and the disadvantages of this method. So it's a first order algorithm. So you're only using the gradient to kind of do your kitchen. And it's not using like this Hessian matrix, so second order information, which usually makes computations way faster. So it's never going to compete against like MOSEC to do some SDPs, but it will be way more robust in the sense that if you go for like higher dimensions, at some point MOSEC is just crashing or it's just requiring too much memory. And those approaches, like first order methods in solvers like SCS, Cosmo, and so on, and this Frank-Wolfe based approach, they actually scale well for high dimensions. And high dimensions, there was last year a paper solving an SDP with Frank-Wolfe, an SDP of size 1 billion. Sorry, million, 10 to the 6. Yeah. So it's not faster, but it's potentially more robust and more suited to large scale optimization.
Oh, that's good.
Thanks a lot for all your comments and questions.
No problem.
So if there is no more question, no more comment, let me finish the seminar. Thank you very much, Sébastien, for delivering a very nice talk.